Today we're going to look at section P.6, which is all about rational expressions. So today we are going to simplify a rational expression and find excluded values from the domain, as well as perform operations on rational expressions. All right, rational expressions. We have dealt with these in the past, but we're just going to continue practicing a little bit more with this today. So a rational expression is a quotient of two polynomials. Essentially, you have to have a fraction with a variable in the denominator in order to consider it a rational expression. Okay, so the set of real numbers for which an algebraic expression is defined is called the domain of the expression. Because we have a fraction, we must exclude numbers from the rational expression's domain that make the denominator 0. Once again, this is something that we've already done in the past. We did this back in chapter 2 when we were talking about domain and range of different functions. So remember, anytime we have a fraction, we never want the denominator to turn into 0, and that's why we were finding excluded values. All right, so let's look at a couple of examples. It says find all the numbers that must be excluded from the domain of each rational expression. So when I'm looking at this first one, I have 7 over x plus 5. So to determine what my excluded values are, I look at my denominator. I notice that this denominator does not need to be factored or anything like that, but my excluded value is going to be me taking that denominator, setting it equal to 0, and determining what is going to then make that x value turn into then that expression being 0. So in this case, all I have to do is subtract 5 from both sides. And so we get x to equal -5. So as far as then what my excluded value is, x cannot equal -5 in order to then be in my domain, or for everything else then to be in my domain. In the second one, notice that x squared minus 1 is my denominator. So what I want to do is I want to, once again, set it equal to 0. In this case, technically x squared minus 1 is factorable. I can factor that into x plus 1 times x minus 1. So then I could set each of those factors equal to 0. And that's why in this case, I'm actually going to have 2 excluded values. I'll subtract 1 from both sides over there. I'll add 1 over here. And so that means that the values that I do not want for x in my domain would be -1 and +1. Okay, if you decided not to factor that, that's perfectly fine. You could just set x squared minus 1 equal to 0. Notice that then I would add 1 to both sides. I would get x squared to equal 1. And then when I take the square root, I would have 2 answers, both positive and -1. So 2 different ways in this particular problem. It is, though, a good idea to factor, just because what we're going to talk about in a second is about simplifying. And so you want everything to be as factored as possible in order to simplify. So while that second option that I showed you works, I would suggest factoring. Okay, so that gets us into the idea of simplifying. So a rational expression is simplified when its numerator and denominator have no common factors other than 1 or -1. So here are my steps to simplify. Factor the numerator and denominator completely. That's why in that last example, I would highly suggest that instead of setting that equal to 0 and doing the square root method, we factor it first. Because then if there's something in the numerator that's also in the denominator, if they have any common factors, we can then divide them, because then it'll essentially simplify down to 1. So any factor that's in the numerator that's also in the denominator, we'll be able to get rid of. So let's take a look at some examples. We've got x cubed plus 3x squared all over x plus 3. So if I want to simplify this, I want to factor the numerator and denominator completely. So first thing we do when we factor is always look for a GCF. In my numerator, looks like there is one. There's an x squared in common with both of those terms. That would leave us then with an x plus 3. If I look at my denominator, x plus 3, there's nothing in common there. I like to then keep it in parentheses, meaning that I check to see if there's a GCF. There isn't. If you want, you could technically put a 1 out in front because that's the GCF that got taken out because it didn't change anything. So notice that once I've factored everything as much as possible, I notice that there's something in the numerator that's also in the denominator. Both of these have a factor of x plus 3. So that means they get to then divide out. And so that's why I didn't technically have to write the 1. There's nothing else in my denominator. So I simplified it. My answer is x squared. If I want to simplify the next example, x squared minus 1 all over x squared plus 2x plus 1. Once again, to simplify means I want to factor completely. The numerator is factorable, just like one of our previous examples. This is a difference of 2 squares. So it's x plus 1 times x minus 1. In my denominator, that is a trinomial that is factorable. Because there's no lead coefficient, I'm just asking myself what multiplies to 1 but adds to 2, and that would be 1 and 1. So we'll have x plus 1 times x plus 1. So everything on the top is factored, everything on the bottom is factored. I see that there is something on the top that is on the bottom, but I can only take as many away as there are on both the top and the bottom. So since there are 2 x plus 1s on the bottom, but there's only 1 on the top, I can only remove 1 from both the top and the bottom. So that means that I'm left with an x minus 1 on the top and an x plus 1 on the bottom. Those are not like factors. So that means that this is as simplified as possible. So then that would be my answer. So I would suggest that you pause the video and simplify this rational expression. So hopefully you noticed that the top is a difference of 2 squares. The bottom had a GCF. And so I was able to take out the x minus 5s. And so that leaves me with x plus 5 all over 7. Okay, I guess I haven't been talking about it, but I put it in my answer here. So if we wanted to go back and look at numbers that had to get excluded, notice that in my original denominator, once you have everything factored, once again, you can then ask yourself, okay, well, what's going to turn my denominator to 0? There's 7, that GCF didn't have a variable, so I don't need to set that equal to 0, but the x minus 5 I did. So that's why x cannot equal 5. That gets excluded. So if I go back here really quick, notice that even though in my first example, the x plus 3 in the denominator got taken out, if I then wanted to find what my original excluded value is, I know that my domain cannot contain -3 because that's what would make my denominator 0. In my original factored denominator, x plus 1 times x plus 1, if I set each of those factors equal to 0, it's going to give me the same result. It's going to give me that x cannot equal -1. You only have to write that one time, even though there's 2 of the same factors there. All right, let's talk about now some operations. Let's look at multiplying rational expressions. So here are my steps. Just like when we simplified, we're going to factor the numerator and denominator completely. When you multiply fractions, you multiply straight across. That's the same thing here with these rational expressions. So we'll multiply straight across, keeping everything factored. So I don't want to then multiply everything out. I want to keep everything factored, but then I just essentially making one big fraction. Once that's the case, then anything that's in the numerator that's also in the denominator can then get simplified and taken away. All right, so let's look at multiplying and simplifying these. So the first example, we have x minus 7 over x minus 1 times x squared minus 1 over 3x minus 21. So if I look at the first fraction, if I look at the numerator, x minus 7, there's nothing that I can do to factor that any further. So I'm going to keep it in parentheses. That indicated to me I looked to see if I could factor, I just couldn't. Same idea with the denominator. X minus 1's not factorable, but I'm going to put it in parentheses so I know, hey, I checked. I just couldn't factor that. The second numerator is factorable. X squared minus 1 is really x minus 1 times x plus 1. If I look at my denominator, that 3x minus 21 is factorable. They both have a GCF. So I can take out a 3, and that would leave you with an x minus 7. Okay, so that was step 1. We factored numerators and denominators completely. Step 2 is we multiply straight across. So essentially with everything factored like this, if you want, you can think of it just as like one big fraction. So now all 3 of those factors are on the top, and then these 3 factors are on the bottom. So now what's in the numerator that's also in the denominator? Well, an x minus 7 and an x minus 1. So then that leaves you with an x plus 1 on the top, and that leaves you with a 3 in the denominator. I can't simplify that any further, so this is my answer. Had there been like more than one number in the denominator, then like say that there had been like maybe a 2 out in front of that first denominator, you'd multiply those numbers, and so then it would have been 6. Okay, so that's how that would work. When we're multiplying straight across, if there's more monomials, multiply them together. Okay, and then just realize that if I was to look for excluded values, it'd have to be everything that's in my denominator. So it looks like in the first original denominator, I could not have x equal positive 1. And then in the second denominator, only that x minus 7 contains an x. So if I set that equal to 0, it looks like then positive 7 also would have to get excluded from my domain. Okay, if I look at the next problem, x plus 3 over x squared minus 4 times x squared minus x minus 6 all over x squared plus 6x plus 9. Okay, go through it. I want to factor everything as much as possible first. So x plus 3, there's nothing to factor there. I'm going to put it in parentheses. In my denominator, x squared minus 4 is going to factor into x minus 2 times x plus 2. If I look at the next numerator, that trinomial is factorable. I can find numbers that multiply to -6 but add to -1. That would be x minus 3 times x plus 2. My denominator is also factorable. X squared plus 6x plus 9 factors into x plus 3 times x plus 3. Once I have everything factored, I can technically think of it as one big fraction where I have 3 factors in the numerator and 4 of them in the denominator. So what's in the numerator that's also in the denominator? Looks like there is an x plus 3 in both the numerator and the denominator, and it looks like there's an x plus 2. So that's going to leave us then with an x minus 3 on the top. And then we still have 2 factors in our denominator, so I'm going to keep those as factors. And so I'm not going to multiply the denominator any further. This would be my final simplified answer. But since we had 4 different original factors, all of which contained an x, I know that I need to set each of those factors equal to 0. So it looks like positive 2 is taken out of the domain. That's an excluded value. So it would be -2. The last 2 factors happen to be the same, so I would just need to set one of those equal to 0, and it looks like -3 would be excluded from my domain. All right, let's talk about dividing rational expressions. Anytime we're dividing fractions, we always want to think about division as multiplying by the reciprocal. So that's the first step. Change division to multiplying, and then we change the second fraction by flipping it around. Then it's a multiplication problem, so we'll just follow the steps for multiplying. We factor everything as much as possible, then we make everything turn into one big fraction by multiplying straight across, and then we simplify. So let's take a look at this example. So we're going to divide and simplify. So we've got x squared minus 2x minus 8 all over x squared minus 9. That's going to be divided by x minus 4 all over x plus 3. So if we want to start, I want to change division to multiplying. So we're going to really then have this first fraction stay the same. But I changed division to multiplication, and then I'm going to take that second fraction and do the reciprocal. So now it's x plus 3 on the top and x minus 4 on the bottom. All right, so now I can go ahead and I can factor. So my first numerator, I want to factor what multiplies to -8 but adds to -2, and that would be x minus 4 times x plus 2. In my denominator, x squared minus 9 factors into x minus 3 times x plus 3. In the second fraction, looks like that numerator is not going to be factorable, and neither is that denominator. So multiply fractions straight across. I can think of it as one big fraction. What's in the numerator that's also in the denominator? Looks like an x minus 4 is, as well as an x plus 3. So that's going to leave us then with an x plus 2 on the top and an x minus 3 on the bottom. And that would be my divided answer. Okay, I'm trying to look to see. It doesn't look like we have to name excluded values for any division problems. So we are going to just move on to the next example. So go ahead, pause the video, and try this checkpoint problem. I want you to divide. All right, so I changed division to multiplying by the reciprocal. I factored completely. I thought of it as one big fraction, so what was on the top, that was also on the bottom. Notice that x squared plus 1 was not factorable, but there was that binomial in both the numerator and denominator, as well as an x minus 1. So I guess here I did write my excluded value. So let me just talk about that really quick. So when you have division, you have to look at not only the original denominators, but then you have to look at the new denominator when you created that multiplying by the reciprocal. So that means that you have to look at the excluded values for these original denominators, but then notice that I have another denominator when I flipped it around. So that's why 0 doesn't work, because that affects that very first denominator of x cubed plus x. The moment I plug in 0, it's going to be 0 plus 0, so 0 cannot be my denominator. Notice that if I was to set then my second denominator, well, that second denominator would be imaginary numbers, because if I try to set that equal to 0, it would be plus or minus I. So we only need to exclude real numbers from our domain. And then if I look at this last denominator that I highlighted, this x squared plus x minus 2, notice that that factored in x plus 2 times x minus 1. And so that's why 1 and negative 2 were also excluded from the domain. Okay, so that's how it would work. It would be your original denominators as well as your new denominator when you flipped that reciprocal. But remember, we're talking about excluding domain of real numbers. And so that's why that second denominator, actually, we didn't need to, at the end, put that excluded value because they weren't real. Okay, so that's us simplifying rational expressions, finding excluded values from the domain, and then performing operations. We did multiplying and dividing.